Okay, in section 10, we're going to look at forced mechanical vibration, where in the last section, we were looking at mechanical vibration or oscillation when we didn't have an external force pushing on it. So if we have an external force, then we're of the format mass times acceleration plus v times velocity plus k times position or stretch, and that equals the external force. And the external force in this situation is going to be a sinusoidal or a cosine function. F0, basically initial force, cosine gamma t. So remember that when we have, excuse me, our solution is a combination of the homogeneous solution and the particular solution. So the homogeneous solution is what we looked at in the last section when we have no external force, and that was a e to the negative b over 2m times t times sine of square root of 4mk minus b squared over 2m t plus phi. And remember, a and phi are just constants. Phi has to do with the phase shift. At what part of the cycle are we starting? A has to do with the amplitude. So to get the particular solution, we have to look at the external force. So our particular solution is going to be of the form A1 cosine gamma t plus A2 sine gamma t. We did that in previous sections. So we get our first derivative of that. The derivative of cosine is minus sine times the derivative of the inside. So we have minus A1 gamma. The derivative of cosine is sine, so sine gamma t. The derivative of sine is positive cosine times the derivative of the inside, so we'll have A2 times gamma cosine gamma t. So now let's get the second derivative. So the second derivative, the derivative of sine is cosine times the derivative of the inside, so we'll have a minus A1. The derivative of the inside is gamma. We have a gamma here, so gamma squared cosine gamma t. The derivative of cosine is minus sine, so we end up with a minus A2 gamma squared sine gamma t. So if we substitute that into our differential equation, we're going to have m times each of those, so minus m A1 gamma squared cosine gamma t minus m A2 gamma squared sine gamma t, and then b times each of those, so minus b A1 gamma sine gamma t plus A2b gamma cosine gamma t, and then k times our yes, so plus k A1 cosine gamma t plus k A2 sine gamma t, and that should equal f cosine gamma t. So we need to collect some like terms. We want to put our cosines together, and we want to put our sines together. So our cosines are these terms. So for cosine gamma t, our coefficient has a minus m A1 gamma squared. We have a plus A2b gamma. And we have a plus KA1. So that's the coefficients of cosine. So then if we do the coefficients of sine, we have a minus ma2 gamma squared. We have a minus ba1 gamma. And then we have a plus ka2. And those are the coefficients of sine gamma t. So we have a f is the coefficient of cosine on the right, so that should equal this. F needs to be whatever that is, and let's combine those. Let's put this in terms of a1 and a2. So a1 is k minus m lambda squared. The coefficient of a2 is b times gamma. That's the coefficient of a2. We don't have any cosines on the right, so the coefficient of sine needs to be 0. No sines on the right, so this needs to be 0. So 0 needs to be, if we sort these in terms of a1, we have a minus b gamma. That's the coefficient of a1. And then the coefficient of a2 is k minus m lambda squared. And we can solve that system of equations by using Cramer's rule. Our general determinant, if we take this coefficient times that one, we'll have k minus m gamma squared times itself minus this product, so this coefficient times that one. Well, if we're subtracting and that's negative, we end up adding b gamma times b gamma, so b squared gamma squared. Now, our determinant for a1, if we replace the coefficients of a1 with f and 0, then imagine that's f and that's 0, then we're going to have f times k minus m gamma squared minus 0 times this coefficient, which is 0. And then the determinant for a2, if this time we imagine replacing this with f sub 0 and this with 0, then our determinant is going to be this coefficient times that one, which is 0, minus this product. So negative times positive is negative. If we're subtracting a negative, we're going to be adding. So that would be f sub 0 beta, or b times gamma. So that means our a1 is going to be f times k, and that's f sub 0 times k minus m gamma squared over the original determinant, which is k minus m gamma squared plus b squared gamma squared. So that's a1. a2 is f sub 0 b gamma over that same thing, k minus m gamma squared plus b squared gamma squared. So now that we have a1 and a2, then our particular solution is a1 change colors to try to make this easier on myself. So we have that times cosine gamma t, and then we have the other one, f0 b gamma over the same denominator, and that's the coefficient of sine gamma t. So we have some things in common that we can factor out. So our particular solution, both terms have that and f sub 0. So if we factor f in the denominator out, we're left with k minus m omega squared cosine omega t. And then if we take that f and that denominator out from the second term, we're left with b gamma sine gamma t. Now we did something in the previous section where we took a cosine plus a sine and we added those together, and we ended up with an a sine, and in that case we had omega t plus phi. But here we're going to have, instead of omega t, we're going to have gamma t plus phi. So from our sum identity for sine, we're going to have sine gamma t cosine phi plus cosine gamma t sine phi, and that a is distributed times whatever that is. So a there, a there. So if we rewrite this as a cosine phi sine gamma t and a sine phi cosine gamma t, phi and a are just coefficients. In order to find out what this simplified version is, we need to know what a is and what phi is. So what we did last time is we replaced a cosine phi with a C1, and we replaced a sine phi with C2, and then we solved this system of equations for a and for phi. So if we get sine by itself, remember we had that sine was C2 over a, and cosine is C1 over a, and we know that sine squared plus cosine squared equals 1. So that gave us C1 squared over a squared plus C2 squared over a squared equals 1. If we solve that, that total C1 squared plus C2 squared is a squared. So a is the square root of C1 squared plus C2 squared, where let me see. So C1 is a cosine phi. So let's see if I use this. So let's see. The cosine gamma, that was this one. I guess it is technically. So C1 and C2. So we end up with, let's see if we can copy this. So since we're changing what's on the inside to a times sine gamma t plus phi, or I think they use theta in this case, a is the square root of k minus m gamma squared plus b squared gamma squared. And then out front we have f naught over k minus m gamma squared plus b squared gamma squared. Notice that this expression and this expression, what's underneath the radical, are the same. So on the bottom we have that to the first power, on top we have it to the 1/2 power. If we're dividing and our bases are the same, we subtract our exponents, so 1/2 minus 1 is negative 1/2. So we're going to end up having that square root on bottom times sine of gamma t, not yt, but gamma t plus, and they're using, I've been using phi here, but they're using theta here because we use phi for the homogeneous. So that means our solution is the sum of the homogeneous a e to the negative b over 2m t times sine square root of 4mk minus b squared over 2m times t plus phi, and then that's plus the particular solution f naught over the radical times sine of gamma t plus phi. So that's kind of messy, and that's not y naught, that's just our general solution. Keeping in mind here, we didn't mention what theta was. Theta, or tangent of theta, is a1 over a2, which is k minus m gamma squared over b gamma. So if we look at our final solution, then we began by maybe thinking about this as a spring solution or a spring system that was underdamped. So it's allowed to oscillate. So why do I know that it's underdamped? Because remember, if it's underdamped, then for our homogeneous, we end up with a sine and a cosine, which combines to this, so it oscillates. But if it's critically damped or overdamped, then we don't get this oscillation term. So we get this oscillation, but notice what happens as time goes to infinity. If time goes to infinity, we have e to the negative infinity, which goes to 0. And as you recall back from the previous section, over time, if we have an underdamped situation, even though it's oscillating back and forth, the peaks are getting smaller and smaller and smaller until it goes towards 0. So the homogeneous part goes to 0 over time. So what you're left with as t goes to infinity is just f sub 0 over the square root of k minus m gamma squared plus b squared gamma squared times sine of gamma t plus phi, which, remember, this part is a result of the external force, the driving force. So over time, as this goes to infinity and that goes away, we refer to that part as the transient part of the solution. It's leaving, it's moving. So if we look at this remaining part, the amplitude is given by that part. So it's related to that initial force, and it's proportional to 1 over the square root of k minus m gamma squared plus b squared gamma squared. And we refer to that as the gain frequency or the gain factor. And notice it's got a gamma in there, which affects the period. Our external force gamma remember the period is 2 pi over that coefficient. So gamma is related to the frequency of the external force or the period of the external force. The frequency would be gamma over 2 pi. So what's left, this is referred to as the steady state. Because this is what remains. After the transient term goes away, then this part of the function is left remaining. So over time, even at the beginning, we have some different oscillations and things going on. We are going to be oscillating, but at a steady value towards the end. Notice in this piece out front, there's not a t. So the amplitude is not affected by time once the transient part goes away. That amplitude is affected by time because that coefficient has t in there, but this coefficient doesn't have time, so this amplitude, after a while, once that's gone, that amplitude remains constant or it remains steady. So after we reach that steady state, this is what our amplitude is going to look like. We will try to come back and look at some examples, but let's continue on and look at the curve of how this gain factor, how it is affected by the frequency of the driving force and some things that are related to it. So our gain factor, 1 over the square root of k minus m gamma squared plus v squared gamma squared. Again, we call that our gain factor. What I think about is gain, if you've ever run sound or used something with an amplifier or just even a radio, the gain is basically your volume. So if you turn it one way, it increases the sound level. If you turn it another way, it decreases the sound level. So remember, that's the coefficient that goes along with the initial force. So depending on what that denominator is, that's going to affect, are we magnifying that initial force, or are we dampening, weakening that initial force? So if we look at a graph of this, this is what's known as the frequency response curve or the resonance curve. So one thing we might be interested in or need to know is, when is that going to be as large as possible? Because if we make the gain as loud as possible, if you take your knob on your radio and turn it up all the way, that can cause problems. If we have some situation that's oscillating, whether it be a bridge that's bouncing back and forth, or whether it be a pendulum that's swinging back and forth, or something connected to a spring that's oscillating, if that gets out of control, then it can cause some serious damage. Another example that may come up in a minute is we've all seen glass break. And what happens when glass breaks with a tuning fork or a sound is that a sound replicating that resonant frequency occurs. So the oscillation caused in the particles of that glass, the amplitude of that vibration is as large as it can be. It's maximized. So if you have something that's brittle like glass and it's oscillating and those oscillations get big enough, then it can cause a tear. So we want to find out, how do we stay away from that that resonant frequency, or that frequency that causes us to have the largest gain. So just like anytime we want to find a maximum, we need a first derivative. And for time's sake, we would use, to take the derivative of that, of course, that would be a chain rule problem. We would change that to the negative 1/2 power, have to use a chain rule. But when the book simplifies it, we end up with negative 2m squared gamma times gamma squared minus k over m minus b squared over 2m squared. That's the numerator. On bottom, we have our k minus m gamma squared squared plus our b squared gamma squared, and that's to the 3/2 power on bottom. If you think about that's to the 1/2 on bottom, or that's to the negative 1/2, when we take the derivative of that, we bring the power down. We do that to the 1 less power. When we move that back to the bottom, that's where the 3/2 comes from. The stuff on top comes from the derivative of the inside. If we're going to have maximums or minimums, remember those are critical points. The variables in this, or the variable, is gamma. Mass is a constant, the spring constant is constant, and the dampening force is constant. The only thing that's changing in this is gamma. So critical points occur where our first derivative is 0. So if we have a product, so this anytime we have a fraction, in order to make it 0, it's when is the numerator 0. So to make the numerator 0, we have a product. So when is 2m squared gamma equal to 0? If we saw that for gamma, that's, well, when gamma is 0. Well, remember, gamma, that's basically the frequency, or tied to the frequency. So that's when our external force is not oscillating, when there's no vibration. So that's in the static state. Well, if that's in the static state, that might tell us what kind of extreme we have there. So the other time is, when is this, the other thing that could give us a critical point is when this factor equals 0. So if we set the other factor, we set that one equal to 0, we add this to both sides, so not y, but gamma squared equals positive k over m minus b squared over 2m squared. So square root of both sides. So that's the other critical value. So if it's not static, if we do have a driving force that's oscillating, then that's our other critical value. And it can be shown that that is a maximum. So that's when our resonance, when our oscillation has the most gain possible. So largest gain factor, meaning that our steady state oscillation is at a peak amplitude. So that's the criteria that will give us that particular situation. So what does that have to do with anything? So the way this will come into effect is, if we want to stay away from having the largest resonance, that peak amplitude, then we might have to adjust something such as the spring being used in our system that's stiffer or weaker, or more likely, we might have to adjust what we're using to dampen our oscillation. If we talked about dampening springs before, if we might put something on here to catch more or less air, and we might have to tune that so that we get the correct amount of dampening so that we stay away from having that peak oscillation, or that we might need it. If we're trying to use, for example, sound waves to break glass, we might want to find that frequency, so we might have to adjust until we get just the right resonance. All right, so this max gamma that we found, we refer to that as the we use that to find the resonant frequency. And another way of writing this, if we get a common denominator of 2m squared, would be 2mk minus b squared over 2m squared. So that's an alternative way of writing gamma sub r. If we substitute that back into our function m for our resonance curve, that's going to simplify to 1 over b times the square root of k over m minus b squared over 4m squared, or you might call that 1 over b. If we get a common denominator of 4m squared, we would need a 4m here. So that over 4m squared. So either way that we want to write that. Of course, if we have a fraction under the square root, we could take the square root of that denominator as well. So I guess that would be 1 over b over the square root of 4mk minus b squared. The square root of that would be 2m. Instead of dividing by the radical, we can multiply by the reciprocal. So if we multiply by the reciprocal, we're going to have 2m over b square root of 4mk minus b squared. So under this particular gamma, and this is what that function would look like, what that curve would look like. And it turns out that the period of that, so the period we said is 2 pi over gamma. And then the frequency, if we want to know how fast do we need it to oscillate, why do we need to know that? If we're breaking glass with sound, then we need to know what frequency, what pitch our particular sound needs to be. Does it need to be an A, a B, a D, an E flat? What frequency do we need? So that's the reciprocal of that. So that's gamma over 2 pi. So I've put together some plots in MathCAD where we plot the resonance curve, and for simplicity, let's let the mass and let's let k both be 1, and let's see what happens as we adjust b. So let's begin by looking at a b value, let's suppose of 2. Notice in this situation, inside our interval, there is no maximum. Well, how can that be if we found over here critical points and we found out where a maximum would occur? Let's see what. So if we look in here, if b squared is more than 2mk, in the numbers we just picked, m and k are both 1, so that would be 2. If b is 2, that would be 4. If b squared is more than 2mk, we get a negative number underneath there. and we can't take the square root of a negative, so the second critical value is imaginary. So the only critical point we have is when gamma is 0. So in that case, no peak there. But as we change b, let's say we let b be 1/2, then notice we do have a peak here. Notice if b is 1/2, 2mk, if we're letting m be 1 and k be 1, that's still 2. But if we let b be 1/2, 1/2 squared is 1/4. If b squared is bigger, we're taking, did I say that right? This is not true. 2mk is bigger, so if this is bigger and we subtract a smaller number, that's positive. So we do have a critical value this time, and here's where that critical value is. That's where that maximum occurs. If we let b change to, let's say, 1/4, then our peak is higher. Remember, m is our gain. So that means there is a gamma here that's going to give us an amplification of 4 times. So whatever our force to begin with, our external force was, then our gain factor is going to be 4 times that. So if our mass is 1 and k is 1, but our dampening is only 1/4, then we have the potential for a certain frequency to have a really strong amplitude. If that gets, if b is smaller, then there's very, very little dampening. So our gain is even bigger. We have a gain almost of 10 there. So in closing, let's summarize a few things. So our solution, remember, is a sum of the homogeneous and the particular solution. Our homogeneous is a e to the negative b over 2m times t sine the square root of 4mk minus b squared over 2m plus phi. So that's our homogeneous. Our particular solution is f over the square root of k minus m gamma squared, m gamma squared, then that squared, plus b squared gamma squared times sine gamma t plus theta. And again, remember, these are not necessarily in the same phase. They could be reaching amplitude at different times, or they could be starting at different locations. So we said that as t goes to infinity, the homogeneous part goes to 0. So we call that the transient part, or the transient term. And as t goes to infinity, then the steady state is f sub 0 over the square root of k minus m gamma squared plus b squared gamma squared times sine of gamma t plus phi, or plus theta. Remember that our external force that's driving this is f naught cosine gamma t. So gamma is related to that external force that's driving the system, driving the oscillation, whether it be a sound wave driving vibration, whether it's something pushing and pulling on a spring. Let's suppose we have a spring attached to a mass, but then on this side, maybe that's attached to a motor that's spinning. So that's, this point is moving. So we have a oscillating back and forth on this end, as well as this mass, when you pull the spring, is oscillating. So after the oscillation that would occur without a driving force, after that dampens away, then all you're going to be left with is the oscillation caused by this external force. So that's what's driving it. So the steady state comes from here. And then we call the gain factor, if F sub 0 is the magnitude or the amplitude of our external driving force, then 1 over the square root of K minus M gamma squared all squared plus B squared gamma squared, that's how much that is increased or decreased by. So what we saw here is that as B gets smaller, then the maximum gain increases. It's still related to what our frequency is, and our frequency is gamma over 2 pi. So depending on which gamma you pick, if you pick a large gamma, then that means your frequency is really small, is really fast, and that's not really going to that's going to overwhelm your system. If your frequency is too slow, then that's not going to have too much of an effect on your system. Your multiplier is just going to be 1, so essentially your force is your external force. But if you find just the right frequency that's not too fast or not too slow, then you can cause really large amplitude growth or really large gain.